So this lesson is a brief review of linear dynamics, especially from a calculus standpoint. It doesn't cover rotational dynamics, just linear dynamics, so it'll be very brief. Okay, dynamics basically covers the aspects of force, momentum, and energy, and we'll be looking at them from a calculus viewpoint, as well as some experimental aspects associated with these topics. So from a calculus viewpoint, Newton's three laws are going to continue to be important. With calculus, force no longer needs to be a constant. Okay, it could be a function of time or a function of distance, similar to the F equals kx for a spring. Okay, since force is no longer constant, acceleration will no longer be constant. And using integral calculus, I can now calculate velocities, impulse, or work without having to worry that my force is not a constant anymore. So as a function of time, okay, when net force is no longer constant, your acceleration is no longer going to be constant. But your acceleration equals F net over m still applies. That's Newton's second law. So if I integrate this with respect to time, I can get velocity. Okay. Impulse, remember, impulse is the integral of force times dt. When force was a constant, we had our Ft formula that we used, okay, but now it's integral of force, okay, it's force for each little section of time, okay, and so if we have a graph, okay, then I can calculate impulse via the area under the curve of that graph, okay, and if necessary, don't forget that impulse also equals the change in the object's momentum, not the momentum because I probably had an initial momentum, okay, but the change in the object's momentum. When force is a function of distance, similar to that spring equation I mentioned earlier, okay, I can now integrate my force with respect to distance to get work. Okay, so at the bottom of this, we see that work is equal to the integral of F. There's that dot there, dx. Okay, that dot is actually a vector dot product. Okay, there are two ways to multiply vectors. Okay, since x or position is a vector, I need to multiply them as vectors. And the dot product is one way. We'll also talk about the cross product in a later PowerPoint. But the dot product is discussed above. Hopefully you know that, okay? But really, all we need to talk about for the dot product is that it's the magnitude of A times the magnitude of B times the cosine theta. Okay, so that's where we get the formula FD cosine theta. Whenever you see that cosine theta, you can usually expect to see a dot product involved. When it comes to the cross product, if you see a sine theta, okay, that's a good indication that a cross product was involved. Okay, so remember that work is also going to be equivalent to the change in the object's kinetic energy. Okay, if the object's kinetic energy is not changing, there must be other forces at play. Okay, and so conservative forces like gravity or electricity and magnetism will change potential energy-wise. Okay, and these forces are going to frequently be in the opposite direction to the applied force, like when you have a rope lifting a bucket at constant speed. And so the potential or the change in the potential energy is going to be equal to the opposite of the work. Opposite or the minus of the work. Okay, and don't forget also that friction will frequently convert kinetic energy into thermal energy. Okay, not that thermal energy is a part of the AP Physics C, but it does steal energy from your system. Okay, when it comes to force experiments, most force experiments will use force sensors or measure mass and acceleration via kinematics. Okay, so most energy experiments are going to use are actually going to measure potential energies because they're a lot easier to measure. Okay, it's easy to measure max height of an object or the initial height that I drop something at. Okay, similarly, it's pretty easy to measure how much I press my spring before I let it go. Okay, it is also possible to measure velocity through kinematics methods to get kinetic energy. Okay, thank you very much.